Okay guys, my name is Vijal and I'm going to show you how to solve question 6 of the International Maths Olympiad 1988. It was a day 2 challenge and question number 3 on the second day, i.e. number 6 in the Olympiad. So it says let a and b be two positive integers such that a dot b plus 1 divides a squared plus b squared, and you have to show that a squared plus b squared over ab plus 1 is a perfect square. So let's see how we do that. We'll obviously solve this problem, and then I'll give you some examples as well. Right, now the way to solve this problem is to write the problem out like this. A squared plus b squared over ab plus 1 equals capital N. A, b, and n are members of real and positive integers. So the first thing to notice is when I rearrange the equation, I get this, which then rearranges to equations 2 and 3. And equations 2 and 3 are identical. I've just moved a squared in front, or b squared in front. So let's just look at equation number 3, where I've got b squared in front. B squared plus the negative na times b plus brackets a squared minus n equals 0. Well, that is a quadratic equation, so b is equal to minus of obviously minus that term there, plus or minus square root of that term squared, minus 4 times 1 times that, divided by 2, and I get b is equal to na plus or minus the square root n squared a squared plus 4n minus 4a squared over 2. Equation number 4. Now just put that equation here again. And the thing to notice is as follows. We're going to concentrate what's in that dotted line over there. So if I expand that, then I can complete the square as follows. Na plus 2a, so plus 2 of a squared minus 4a squared minus 4a squared. And we get this equation over here, which is identical to that. Essentially, I'm just taking the common denominator as a squared out of the equation, so we get the final equation as that being identical to 1 over a squared na plus 2 squared minus 4 lots of 1 plus a to the power of 4. So therefore b is equal to na plus or minus 1 over a squared brackets na squared plus 2 squared minus 4 1 plus a to the power of 4 brackets. And therefore if I bring that a squared to the bottom, obviously the root of 1 over a squared is 1 over a, and I multiply this by a just to compensate for it, I get b is equal to na squared plus or minus the square root of na squared plus 2 squared minus 4 brackets 1 plus a to the 4 over 2a. So essentially that b, which is over here, can be written like this, with a term in the square root like this, and with the a term underneath here. So that's equation number 5. Now notice that in equation number 5 we have a square term here, and we have minus 4 lots of another term here, and obviously this is a real positive integer, so h to the 4 is going to be positive. Now I want you to have a look at this over here. This is a perfect square. P minus 2q all squared is equal to p squared minus 4pq plus 4q squared, and that is also equal to p squared minus 4q brackets p minus q when you take it out. So to notice here is that is a square, p squared, so that is p all squared. And then we've got minus 4 lots of q brackets p minus q, so we've got minus 4, and we've got here a bracket 1 plus a to the 4, so we're going to use identities. And this is a perfect square if p and q are real positive integers, and we just assume that p is obviously greater than 2q. Now let p be identical to that term there, na squared plus 2, and therefore q, p minus q, which is that q, p minus q, remember there's a minus 4 term there, is 1 plus a to the 4. So therefore, when I rearrange, q times p minus q, it must be identical to 1 plus a to the 4. q na squared plus q2 minus q, so I've expanded that, is 1 plus a to the 4, identical to 1 plus a to the 4. The only way this holds is if q is equal to 1. So where when q is equal to 1, we have na squared plus 1 times 2 minus 1 is equal to 1 plus h to the 4. We have na squared plus 1 is identical to 1 plus h to the 4, and therefore n is equal to a squared. Do you see that n is equal to a squared? Hence, the number n in that bracket there for a given a is a squared, and therefore that proves that n has to be a perfect square in all situations in order for this equation to work, and in order for that to be a perfect square for it to work, and subsequently to give b as a real and positive integer value. Now I'm going to just show you a little bit more. Now this is the use of parametric equation. So let a equal small a, and therefore n is equal to a squared. Therefore b is equal to na plus or minus the root of n squared a squared plus 4n minus 4a squared over 2. This is the original equation number 4 that we had. So if I just go back a bit, that was that equation over there. B is equal to na plus some minus square root of n squared minus plus 4n minus 4a squared over 2. Obviously this was before we then converted that into another equivalent equation, which was number 5. So if you just go to the original b is equal to that, which is equation number 4, then if we put the values of let a is equal to small a, that parameter a, therefore n is equal to a squared, we get this equation there. And that simplifies to a to the cubed plus or minus the root of 86 over 2. So it could either be that, which is a cubed, or 0. So therefore, for a is equal to a, where the parameter is a, n squared is obviously a squared, b is equal to a cubed or 0. Now, we've got b is equal to a cubed. What would happen if we did the same thing, but this time we let a equal the a cubed and n is equal to a squared? Well, we should get b either as equal to a originally, or it would be something else, and we do get something else. We get this over here. So I'm just going to show you how to do that. B is equal to na plus or minus that, which is again equation 4. And when I put these values in, so we have n is equal to a squared, the parameter a squared, a is equal to a cubed, I get this, and that simplifies to that, which simplifies to that. Notice that that is a perfect square inside, so we get this, a to the 5 plus or minus a brackets a to the 4 minus 2 over 2, and that equals that, a to the 5 plus or minus a to the 5 minus plus 2a over 2, and therefore b can either equal a to the 5 minus a, or b is equal to a, which is what we're expecting, because previously when a was equal to a, b was equal to a cubed, and n is equal to a squared. We've now let a equal a cubed, we get n is equal to a squared, we get the original b is equal to a back, but we also get b is equal to a to the 5 minus a. Now let's put that, again, that parameter a to the 5 minus a into the equation again. So reiterate that. When you go through the steps, we get again a perfect square. The root of that is that, and then when we solve for this, we get b is either equal to a squared minus 2a cubed, or b is equal to a cubed, which is what we got last time. So for n is equal to a squared, if a this time is a to the 5 minus a, we get that, which was the original answer, a cubed, b is equal to a cubed, or we get a to the 7 minus 2a cubed. And the thing is, when we reiterate all these formulas in equation number 4, for any n which is a squared, that is a square, and the parameter is a, we get the first value a1 is a, and b1, the value of b, can either be 0 or a2. Now a2 is a cubed, a3 is a to the 5 minus a, a4 is a to the 7 minus 2a, and it goes on. So these are the first 12 polynomial equations when you iterate the formula, and obviously b is either equal to 0 to a cubed, b2 for a2 is equal to a cubed is either a or a to the 5 minus a, either a1 or a3. So whatever value of a you have, whatever value you put small a into here, you get an a5, and then the corresponding b5 for that value would be either this a value here, which is a4, or this value here, a6, and it goes on. So whatever value you have for b, like b of 10, it would be either the a 9 or the A11 value. And obviously A10 would be the A value. So let's have a look at some examples. If, for example, a is 2, then n squared is equal to, then n is equal to a squared, which is 4. So what values of a and b give rise to 4? Well, if a is 2, b is either 0 or 8. If a is 8, b is either 2 or 30. If a is 30, b is either 8 or 112. If a is 112, b is either 30 or 418. If a is 418, then b is obviously either 112 or 1560, and it goes on. So that is how you solve that equation. So this is how you solve to form a perfect square, to show that n is a perfect square, and it is a perfect square with a parameter a squared. And this is how you do it. You obviously look at b, rearrange b to get that, show that that is a perfect square from this, and make an identity to show that n is equal to a squared, which is a perfect square. And then if you use a parameter let a equal a, then n is equal to a squared. You get all the values of b, which is either a3 or 0. And when you reiterate that in the formula again for a3, and for n is equal to a squared, you get b is equal to a, or a to the power minus a. And then you keep on going till you get all the set of polynomials for all the a values and the corresponding b values, which is either, for this value, will be either one above or the one below. And this is all the examples that I've got, so you can continue on. So hopefully that shows you how to prove question number 6, and with some examples to show for the parameter a is equal to 2, i.e. n, which is a square of 2, which is 4. Thank you very much.